Welcome back to my kitchen. So here I have a sink, a cold tap, and a hot tap. The cold water is about, I don't know, maybe 16 or 17 degrees C. The hot water is considerably warmer. Let me just give it a minute to warm up. It's about 40 degrees C. Oftentimes, if you want to have water at a particular temperature, rather than trying to heat up that water to just the right amount of temperature, you're better off mixing cold water and hot water to get just the temperature you want, right? This is how we do all the water in our houses. This is how we take showers at the right temperature. So, if I have two water streams coming in at different temperatures and I mix them together, it's understandable that I get some temperature that's in between the two. 28 degrees C is in between the two temperatures of hot and cold water. So, as engineers, we don't want to just say, well, we could get some temperature in between them. We want to predict things. So, let's go ahead and predict that. So, what's the plan for today's lecture? Today we're going to talk about conservation of energy. And what do I mean by conservation of energy? You're like, hey, wait a second, we already talked about conservation of energy. We did talk about conservation of energy, but that was mostly for fluids and mostly a sort of mechanical energy, right? So we already talked about conservation of sort of mechanical, kinetic energy, talked about kinetic energy and pressure and potential energy for fluids. But if we're talking heat transfer, we're not going to focus on conservation of sort of kinetic energies, because oftentimes the kinetic energy of a fluid is negligible compared to the thermal energy. We're going to be talking about kinetic energy in terms of thermal energy, mostly focusing on thermal energy, right? So if I were, instead of writing this out by hand, if I were typing this out, there would be a little fire emoji right here, because we're talking about heat. And we can break up this process of conservation of thermal energy into a few parts. So what are we going to do? We're going to formulate conservation of energy in the same way that we formulated many other conservation laws. We're going to have a rate as a rate balance. We're going to do the rate of accumulation, and it's going to be sort of control volume based. So the rate of energy accumulation in my control volume is going to be equal to the rate in minus the rate out plus the rate of any heat being generated within my control volume. So I can basically say, hey, yeah, there's a balance. There's rate of accumulation, a rate in, a rate out, and a rate generation. And basically all of these rates need to balance the rate that heat is being accumulated inside my control volume. Then we're going to sort of look at each of these terms more specifically. So we're going to talk about the accumulation rate. We're then going to talk about our ins minus outs. And this is actually going to have a few parts. We're going to break this up into heat carried by a fluid, so when we were looking at my faucet just a moment ago, we had some heat carried in by the hot fluid, some heat carried in by the cold fluid, albeit less of it, and some heat carried out by the mixed stream. So we can basically, we can compare, hey, is there thermal energy actually carried by the mass that's entering and leaving my system? We can also talk about ins minus outs in terms of conduction. And in a sense, we already did that in last lecture, right? We said, hey, there's like these Q dots, Q sub X or Q sub R, right? We talked about these things, to some extent already. So, conduction can be a means by which heat can enter or exit. We could also talk about surface convection, and that's actually going to be this is going to be the focus of a future lecture. And actually, you can have thermal energy sort of being converted into other types of energy if your fluid does work on your surroundings. And I'll talk a little bit more about what that means when we get to that part in the equation. We'll also we'll talk about our ins and our outs. We're also going to talk about our generation term. So we're going to talk about rate of generation and sort of what that might mean in some contexts. Then we're going to say, hey, you know, the general form of this conservation of energy, like that's going to be a little bit messy, and oftentimes it'll be a bit cumbersome to use the entire thing, the entire conservation of thermal energy equation. So we'll talk about typical simplifications. And basically what assumptions might go into those typical simplifications. And then we'll wrap up this discussion with an example problem. And this example problem is going to be similar to the hot and cold faucet that you saw me turn on at the beginning of this lecture. What happens if we have a hot and a cold water stream mixing? So I have a hot stream and a cold stream. They come together. You know, what does the temperature at the outlet look like? You know what is the temperature at the outlet? So this is where we're going with today's lecture. So let's start by putting in this equation where we have a rate of accumulation, some ins and outs in generation. So let's go ahead and put it down. So this is basically, it's defined for a control volume. So it's defined for a control volume, and my rate of accumulation so my rate of energy accumulation, I could sort of put most generally as dE dt, where basically E is the energy in my control volume. So the time derivative of the energy in my control volume is the rate of energy accumulation within that control volume. So this is it. So take a moment now, pause and ponder. What are the units? What are going to be the units in all of the terms in this whole conservation of energy? Well, if you work out the units, right? So energy is going to have units of joules. Energy is going to have units of joules. So our time derivative of energy is going to have units of joules per second, or watts, right? So watts is what we use for joules per second. So, you know, because the left-hand side, our accumulation term, is going to have watts, then all of these other terms are going to have watts as well as their terms. So let's now talk a little bit about, so that's our rate of accumulation, and I'm just going to leave it as something a bit general for now. And then actually, yeah. So I'm just going to leave it as something a bit general for now. So now let's talk about our ins and our outs. So, and in particular, we're going to talk about heat carried by a fluid first. So if I have some control volume, right? Let's think about this control volume right here. And let's say, you know, we're approaching the faucet problem that we talked about earlier. You know, I have, like, let's say a hot stream and a cold stream coming in and then some stream coming out. You know, the amount of energy that, let's say, my hot stream carries in, and I have a cold stream carrying in, the amount of energy my hot stream carrying in is proportional to two things for it. So one thing that the rate of energy going in carried by this hot stream is proportional to is the mass flow rate, right? So if I think about heat carried by fluid, it's proportional to two things. It's proportional to the mass flow rate, i.e. if I have more fluid going in, then there's more energy going in, right? The more more fluid is going in, the more energy is going in, right? The more the more joules are coming in. And mass flow rate has the variable lowercase w that we had earlier, right? So heat carried by a fluid, one of the ins associated with heat carried by a fluid is going to be lowercase w for the mass flow rate of one of these. The other thing is how much energy each unit of mass of fluid has, right? So, I have this hot stream coming in. Each kilogram of hot fluid that comes in has a heck of a lot more energy than each kilogram of cold fluid that goes in. And people oftentimes talk about this in terms of like enthalpies, or enthalpies per unit mass. And basically what people use is a capital H with a little hat on it. So this is what's going in, right? So if I think about units, mass flow rate is going to be have units of kilograms per second, and this H hat is going to have units of joules per kilogram. So when I multiply these two terms together, I get joules per second, which would be consistent with watts, right? So the heat carried by the fluid is proportional to the mass flow rate, but also proportional to this H hat. But I could have, potentially multiple inlets, right? There could be an inlet here and an inlet here. So I'm not considering just one mass flow rate and one enthalpy. I need to sort of consider the fact that there are multiple inlets in here. So I need to basically sum over all of the inlets. And, I might say, I sum over the inlets from, let's say, I equals 1 to the number of inlets. So for this system down here, it would be 2, and there might be a different W and a different H for each of these inlets, right? So sum over, I could call, this inlet, this would be like I equals 1, and I would call this I equals 2. So I'd basically sum over all of the inlets, each of the inlets mass flow rate times each of the inlets amount of joules per unit mass that's going in. And there could be some number of outlets as well, so I would just subtract out the heat that's carried out by the outlets, and it would sort of have a similar form. So maybe I would call this W sub j, just so I could have different subscripts so I don't confuse them, over my outlets from j equals 1 to the number of outlets. And it would be W sub j times H hat sub j. So mass carries thermal energy in, mass carries thermal energy out, and this is essentially part of the ins and outs of my system. But heat carried by fluid isn't the only way that heat could enter or exit this system. I could also have heat carried in or out of my system by conduction. So let's include a term to basically account for conduction. And sometimes what people do is lump together conduction and surface convection into a single term. And what do they call it? They call it Q dot sub S, where Q dot sub S is heat that crosses the control volume's surface, but that's not from mass crossing. That's not from mass crossing the surface, right? So let's say I have my control volume right here, and maybe I have a block of copper kind of sticking through the surface right here. Well, I might have some heat exiting from that conductive copper, right? So my Q dot surface, I could basically say, hey, this Q dot surface could be from one of two phenomenon. I could call it would be a Q dot from conduction plus a Q dot from surface convection. So maybe I could have some heat that's being leached out through a copper bar, or maybe in another scenario, I have like a solid part of my control volume right here. So let's say this part is solid, but then I have some fluid not crossing the surface like it is for these inlet streams, but just kind of flowing against the surface. And in that case, this fluid that's flowing against the surface, this fluid's mass isn't crossing into or out of the control volume, but this fluid that's flowing by the surface could carry away some heat. So that's kind of this phenomenon right here, whereas my conduction, I could have some block of copper that crosses the control volume surface and some heat that's conducted out of that. So my surface, basically, I could break it apart into these two terms right here. Conduction out of the surface of the control volume, or convection out of the surface of the control volume as well. So basically both of these are my surface phenomena. So that does it. I'm going to add one more out right here, and so there we have it. Let me just clarify that actually I drew these arrows a little bit incorrectly. This Q dot surface is basically defined as heat that's crossing into the surface, right? So this is positive, right? So Q dot S is sort of defined as heat that's crossing in. I should have drawn it this way through my conduction. This is sort of, because it's on the right hand side and positive, this is sort of defined as heat that crosses into the control volume surface from mass crossing, but not from mass crossing the surface. But I could just, if heat happened to be leaving, I could just, there would just be a negative input is the same as an output, right? But it's on the right hand side and positive, same as these ins, right? So this is basically a heat flowing in, but you could just, if it happens to be heat flowing out, you could just subtract it instead. All right, so clarified that. Now let's talk about how if we have fluid in our system doing work on surroundings. So if you have an internal combustion engine, there's like a piston and you have basically fuel in here that combusts, right? So there's fire in here, and that hot gas wants to expand, and that hot gas expanding actually, applies force and pushes this piston. So the piston moves this way, the force is applied this way, so basically the fiery fluid, the fiery combustion gases in here actually do work on this piston. And the work that these hot combustion gases do on the piston, that energy, doesn't just appear out of thin air. The energy comes from a transfer of thermal energy of the combustion products into mechanical energy of the work, right? So if we have control volumes, for example, that are defined around things like combustion gases, we need to account for the work that those combustion gases do on the surroundings. So I could include another term here that is like my W dot S, which might look a little bit familiar. We could call this shaft work, or we could call this sort of like basically work that our CV does on the surroundings. Oh, so it's a rate of work that our CV does on the surroundings. So and in a sense there's a minus sign out front because any work that our CV does on the surroundings is an energy output from the system. Spoiler alert, this isn't going to show up too much in biofluids, right? I don't know about you, but I don't really have too many internal combustion engines inside of me these days. So, you know, not showing up too often, but I get ahead of myself. We have one more term in here, the rate of generation. So what might that look like? Well, we could just sort of, we could give it its own variable, q.gen, and we could define it down here. So this would basically be the rate of thermal energy being generated in our control volume. And you might be, hey, wait a second, Professor Landon, I thought energy couldn't be created or destroyed. And the answer is, yes, I guess this isn't really being generated per se, but it's some energy source that's not one of these that is sort of being converted to thermal energy, right? So what might this this generation term come from? This generation term might come from things like chemical reactions, right? So if I have some exothermic reaction, then I'm going to have a Q-gen, you know, burning sugar or something like that is going to be effectively a heat generation within our control volume. So, you know, it might be things like chemical reactions. You know, it might be, you might be able to model it as something like, you know, here I have a heating pad. You know, there's electric heaters inside of here. So, you know, under some contexts, we might say, hey, you know, I could kind of view the conversion of electrical energy, which isn't in one of these terms, to thermal energy from those electric heaters. You know, I could kind of view that as like a Q-gen term here, right? So maybe it's like electric heaters, right? So the, you know, so we kind of put those in the gen like terms. So that's it. So this is our conservation. This is our conservation of sort of thermal energy defined for a control volume. So let's take a closer look at this accumulation term right here. So if I think about this accumulation term, it's d energy dt, where the energy is the sort of total energy of the system. So if I neglect all energy types, except heat, then I can say the time rate of change of energy in my system would be approximately equal to just the time rate of change of thermal energy in my system, right? So if I'm saying like, hey, most of the joules of my system are really the thermal energy joules. You know, yes, there's a 1/2 mv squared somewhere. Yes, there's an mgh. You know, yes, there's kinetic energy. Yes, there's, you know, gravitational potential energy. But, you know, how often do you, like, you know, drop a block off of the top of your house and then say, wow, that block got really hot from dropping it? Like, that doesn't really happen a lot, right? So oftentimes thermal energy tends to be orders of magnitude above these other energy types. So if we're talking about conservation of energy for heat transfer, you know, we don't really have appreciable contributions to any of this from conversion of kinetic energy or potential energy into thermal energy. So, you know, so this isn't a bad approximation. And then if also there's one material type in our control volume, right? So, you know, let's go back to this example here, right? If I consider this example here, and I draw my control volume maybe just around the part of my hot and cold mixer that contains the fluid, you know, then I might say, hey, you know, if there's one material type in our control volume, then I can make a further approximation to this. So if there's one material type in my control volume, then I can basically say, hey, this thermal energy can be expressed as follows, right? So the thermal energy in my system is proportional to a couple of things. So thermal energy, the first thing that it's proportional to is the amount of mass in my system. Right? The more mass I have in my system, the more heat there is. Every kilogram of everything in the universe has some thermal energy stored in it. So the more stuff we have in our system, the more thermal energy is in there. But it's not just mass that contributes to it. Another factor is the average temperature of everything in my system, right? So the hotter my system is, the more thermal energy it has. And then if I think about units, this thermal energy is going to have units of joules, the mass of my system is going to have units of kilograms, and my average temperature is going to have units of Kelvin. The units on the left-hand side and the right-hand side don't match up. So, but I'm feeling pretty good about these proportionalities, right? The more temperature, the more thermal energy, the more mass, the more thermal energy. So the last thing that we need to include in this thermal energy balance is a proportionality factor that relates these. So the last thing is what I'll call Cp. This is what we call the specific heat capacity. And it's something that's a material property. So if my control volume is, let's say, around water, water has some specific heat. If it's around air, air has a different specific heat. If it's around copper, copper has a different specific heat. So basically, it takes different amounts of energy to change the temperature of different materials differently. It turns out that it's actually, water actually soaks up a ton of energy in order to change its temperature. And on a per mass basis, more than aluminum even, or some other materials, right? So basically the Cp is how much energy, so it's defined as the specific heat capacity, is basically how much energy does it take to raise 1 kilogram of the material 1 Kelvin. So it's sort of, it's basically, a material that has a high capacity takes lots of joules to raise 1 kilogram of it 1 Kelvin, whereas a material that has a low heat capacity takes very few joules to raise 1 kilogram of it 1 Kelvin. So if I think about what are the units of Cp, well, its units are whatever it needs to balance both sides of the system, but in this case, it would be it has to have units of joules in the numerator and kilogram and Kelvin. Joules per kilogram Kelvin in the denominator. You might have actually in your high school chemistry or first year chemistry classes, used Cp for some of your, exothermic or endothermic, changing the temperature of a water bath type experiments. And you might have used it, you might have expressed it maybe in joules per gram degrees C. But you can say, it's still an energy per mass and per temperature sort of basis, right? So there'd be a conversion factor between the two. So my thermal energy of this, one thing that I'm kind of sweeping under the rug here is that there's no phase change. So it turns out that this isn't quite true. There can be it requires thermal energy to actually like boil liquid water to becoming a gas or thaw frozen water to becoming a liquid. So this isn't accounting for the phase change. This is just counting for sort of temperature change phenomena. But again, we're not going to cover too much of this phase change business in this class. But what can I do? I can take this and I can plug it in here. So the time rate of change of thermal energy would basically be the time derivative of this product of 3 terms. provided I neglect any energy type that isn't thermal, if there's just one material within my control volume, and I don't have any phase changes of that material in there. So, certainly some assumptions here, but we can get something that is a little more concrete. Temperatures are things that we care about. Mass of the system and CP are things that I can look up or things that I can measure. So rather than sort of dealing with this ethereal energy, which, there's not really like an energy meter that I could put on a system, these are things that are actually measurable quantities. So that's what we have here. Let's sort of investigate these ins or outs a little bit more too. So taking a closer look at these H terms, remember these ins and outs are the thermal energy carried by fluid entering or carried by fluid exiting. So part of the factor was the mass flow rate. The other factor was how much energy each unit of mass has. So what might that look like? Well, I could formulate my H's. I could formulate this H has. This is basically how much energy, how much thermal energy does each chunk of fluid have? Well, I could basically say, hey, this has to have units of joules per kilogram. And if we notice, this H, is basically like the product of these two terms right here. Here I have joules per kilogram Kelvin in Kelvin. So, if I also do this no phase change assumption right here, this H is basically just the temperature times the specific heat of the fluid that I can go in. So if I assume no phase change at the inlet, then basically, the rate, a rate of thermal energy entering from one of the inlets is the mass flow rate times this H, where this H is just temperature times Cp. And of course, I could also, say, hey, my mass flow rate might be a little bit easier to express or measure. I could put it as a volumetric flow rate times density. So, so what's this going to look like, right? This is kilograms per cubic meter. This is meters cubed per second. So this is going to be kilograms per second. So, what might this term look like under some circumstances? Maybe a W times an H hat, under some circumstances might look like the temperature times the specific heat times the volumetric flow rate times the density. And if you carry out all of those units, then you're going to have something that ends up with the product of these two terms is going to have watts or joules per second as its thing. So for a lot of systems, we can express the energy that's sort of carried in by mass coming in from an inlet. We can express it as this product of terms. And you could do a similar formulation for all of your inlets and your outlets as well. So let's look a little bit more closely at some of the other terms in this expression. I have this Q dot S, which is heat flowing in from various surfaces, and I broke it apart into conduction and convection. So surface convection is something that we're going to cover in a future lecture, but recall that conduction is covered by Fourier's law, which we talked about in the last lecture, and it's minus K times cross-sectional area times dt dx, and this would of course be evaluated at the surface, whatever part of the surface of my control volume I'm acting at. So what does this mean? If you have temperature gradients at your surface, then that's going to result in heat flowing into or out of your control volume via conduction, and you got to account for that in your overall energy balance. We'll do surface convection in a future lecture. So very rarely, and in fact I don't think at all, in this class are we going to use this full equation where we have all of these terms going on at once. Almost always we have a system where some or maybe even most of these the terms in this equation we can cross off due to various assumptions that we can make about our system. So let's talk about typical simplifications that can arise and the assumptions that might give rise to those typical simplifications. So I'm going to rewrite this equation here, and then we're going to say, hey, under what conditions could we get rid of, some or some of these terms here. So I have my accumulation equals mass or heat carried by mass from the inlets and outlets, and I'm going to split apart. Whoops. What I had here, I'm going to split apart my surface into conduction and surface convection here. And then I'm going to have my W dot S and my Q dot gen. So under what conditions do I keep or get rid of these terms, and what assumptions are associated with it? Well, let's look at that. If my system is steady, if my system's in steady state, then I can get rid of this term, right? So this would be analogous to, remember how I turned on the faucet and it took a couple of seconds for the thermometer that I had running under the water to get where it was going? Well, if my system's in steady state, then my temperature eventually kind of stabilizes to a particular temperature that is reflective of the flow going in and out. So if my system is steady, then I can get rid of this term. A number of systems that we'll analyze in this class, we can get rid of these terms if no fluid is crossing the boundary of our control volume, right? So, for the problems that we solved in the last lecture, those were solids, right? Basically, our entire control volume, we didn't really define a control volume explicitly, but one was sort of going around in the background. We were talking about heat flow just through solids. So if we're talking about heat flow just through solids, then we don't have any of this business where we have mass entering or exiting. If we have a system where we have very good insulation, covering the sort of solid parts, if the surface of our control volume, if there's very good insulation surrounding that, then we can sort of oftentimes we can neglect heat conduction through very good insulation if some of these other paths dominate over the heat going through our insulation. This surface convection phenomenon is basically, if no parts of the surface of the control volume are at a solid fluid interface. Right, so sometimes we have solid fluid interfaces, and surface convection is this phenomenon by which sort of heat flows just out of the solid and just barely into the fluid, and that's this phenomenon right here that we're talking about. So if we have a control surface that basically doesn't have any of these solid fluid interfaces, then we don't have this phenomenon going on here. This we usually neglect almost always But if our control surface, if we don't have like combustion gases pushing on, if basically like the thermal expansion of things isn't pushing on the control surface. So this we almost always get rid of if we don't have appreciable conversion from thermal energy to work. So if no if we have no thermal energy gets converted to work. And that's almost always going to be a good assumption in the context of this class here. And this generation term, we can get rid of this if there are no chemical reactions, no electric heaters, no radioactive decay, etc. So there we have it. Assumptions that can allow us to get rid of particular terms in this conservation of energy equation. And I guess there was one that I actually already got rid of here. Strictly speaking, you could have surface energy. You could have radiation leaving your surface as well, but almost always we're getting rid of that. This only really happens at low temperatures, right? So moderate surface temperatures basically means no radiation, i.e. we don't have things that are glowing hot like that sword that the blacksmith pulled out of the forge and is bright orange. So these are all the terms that can exist in conservation of energy, and these are all of the types of assumptions that might allow us to get rid of them. So let's do an example problem. And it's similar in some ways to my faucet problem where I had the hot tap and the cold tap, but let's just sort of put it in the context of microfluidics. So let's say I have a microfluidic mixer where I basically have I have two streams of fluid coming in, and I want to predict what temperature they're going to have at the outlet. So I have a little Y channel like this. Let's say there's some fluid coming in here with one volumetric flow rate. I'll call it QV1. And let's say there's another fluid coming in here with a different volumetric flow rate. I'll call it QV2. And let's say we know the temperature of this fluid coming in. This fluid is at known temperature T1, and this other fluid is at known temperature T2, right? So this is basically saying I have a hot tap and a cold tap, and I know what flow rates are going in and what temperatures are going in. I want to be able to predict what's coming out of my system right here. And in particular, I want to be able to predict what the volumetric flow rate is at the outlet. Let's call it QV3, and I want to be able to predict what the temperature is of my system at the outlet. Let's say we have some additional knowns about this system. This channel is filled with water that has a known density and a known specific heat. So let's say these quantities are known, and let's actually put them down here. Let's actually put some specific numbers to these things, right? So let's say QV1 is 1 milliliter per hour, and let's say T1 is 10 degrees C. Let's say QV2 is 2 milliliters per hour, and T2 is 20 degrees C. Water has a density of about 1,000 kilograms per cubic meter, and the specific heat of water is 4.19 joules per gram degrees C. So we have these knowns about the system, and we want to be able to predict what the volumetric flow rate and the temperature at the outlet is. Of course, we need to be given some additional information to solve this problem. So additional information that we are assuming about this problem is the system is at steady state, i.e. these inlets and outlet, the two inlet flows have been going for such a long time that, you know, whatever was in this channel whatever was in this channel initially is long gone, and we've kind of stabilized our flow and temperature at the outlets. We're assuming we have a well mixed. It's basically well mixed. The stuff on the inlets is well mixed, and also the inlet stuff gets basically well mixed by the time it gets at the outlet, right? It's not like we have a little more like T1 down here and a little more like T2 up here. We're basically assuming, hey, these things come in and they mix pretty well by the time they get to the outlet. So basically it's well mixed, which basically results in uniform temperatures at inlets or outlets, right, at each respective inlet and outlet. We're also going to assume that whoever made this microfluidic channel put a lot of insulation they're going to assume that we put a lot of good insulation around the sides of this channel. We're going to assume that the fluid is uniform and incompressible fluid, so we can basically say, hey, these two properties are constant, and we also don't have any reactions, and that the fluid is not doing work on our surroundings. So if we assume all of this stuff about our system, we can proceed with conservation of energy to try to solve this, right? So, you know, when might you use this conservation of thermal energy? You might say, hey, if I have information about energy, you know, energy flowing into my system at various points, but I want to find information about, well, maybe energy flowing out of my system, but a thing that is indirectly related to energy flowing out is, of course, the temperature of whatever is flowing out. So if I basically want relationships between different temperatures of things in this sort of system-like way, I can use conservation of energy to try to relate what's happening at the outlets to what's happening at the inlets. So let's do conservation of energy. So what does conservation of energy look like? Well, we can lay out all the terms. So I have my accumulation term, and I can replace, instead of having the H sub i's, I can replace these H sub i's with the slightly more convenient, formulation in terms of specific heat, right? So I can basically replace the H's with temperatures at times specific heats. So I can do this at the inlets. I can also do this at the outlets. And in this case, the subscript I or the subscript j, you know, we'll have 1 and 2 and 3. You know, those will sort of be the numbers of the inlets and the outlets. You know, in general, we could also have, from conservation of energy, we could also have the following terms. We could have conduction flowing into our system. We could also have surface convection. We could also have work that the energy does on the system, and we could also have generation. So what assumptions can we tie to which things down here? Well, the steady state assumption allows us to get rid of this term. We do have mass. Oh, I guess I should define my system first, right? So let's basically define my system. Let's define my control volume like this to sort of be coincident with these surfaces right here and perpendicular to these flows at the inlets and outlets. So conservation of energy ends up being this way. So I can get rid of this term because we're assuming that we're at steady state. These guys I got to keep. But if the system is well insulated, then I can basically say, hey, there's no conduction or convection through these parts of the surfaces, and my inlets and outlets are basically accounted by what's going on right here. So well insulated walls help me get rid of these assumptions. I can basically, the assumption of my system not doing any work means, I don't have like explosions going on here that are, pushing on the boundaries, doing things like that. And if I assume I don't have any chemical reactions, then I can get here. I can get rid of this term here. So even though we started with something that was pretty complicated, we end up with something that's a little bit simpler. All right, so now let's take these sums and see if we can break them apart into something that's a little bit more helpful. Recall that mass flow rates can be broken up into density times a volumetric flow rate. So that's what I'm going to do in this next step here. So left-hand side is 0. I have 2 inlets, so there are going to be 2 of these. So there's going to be density times my volumetric flow rate at inlet 1 times Cp times T1. And then I'm going to have my second inlet, which is going to be density times the volumetric flow rate at surface 2 times Cp times T2. And then I'm going to have my outlet term right here. So I have a minus sign, right, because it's an outlet. I accounted for both of the inlets, and now I have an outlet. So I'm still going to have density. I'm going to have my as of yet unknown volumetric flow rate at my outlet. I still have Cp. And I have my as of yet unknown temperature at the outlet. All right, great. So we do applied conservation of energy, and that helps us relate temperatures at the inlets to temperature at the outlet. Ooh, but what's going on here? I have 2 unknowns. Yikes. So take a moment, pause and ponder. What are we going to do about this second? How are we going to resolve the second unknown, right? If we have 2 unknowns in our system, we only have 1 equation. What are we going to do about it? Well, hopefully you've had a chance to pause and ponder. If I'm looking to resolve the second unknown, I might be able to get information about this volumetric flow rate at the outlet. Well, the volumetric flow rate at the outlet, again, we assumed uniform incompressible fluid. Whatever volumetric flow rates are flowing in should match the volumetric flow rates out. So basically, if I did conservation of mass would tell me, I'm going to skip the details here because you can go back and do it yourselves. Conservation of mass would basically tell me that the volumetric flow rate out is equal to the sum of the 2 volumetric flow rates in. And then what can we do? We can take this and we can plug it in right here. And when we take this and plug it in right here, then we have 1 equation and 1 unknown. So now I encourage you to pause and ponder. What's T3? So take a moment now, pause the video, ponder, try to work it out. What's T3? Well, if you do the algebra, if you notice all of these terms have rho, so rows, we can divide through everything by rho, and all of them have the same CP, so we can divide through by CP as well. We can sub in the QV1 and QV2 right here, and when you work it all out, you end up with QV1 times T1 plus QV2 times T2 divided by QV1 plus QV2. We could check the units and see that we have volumetric flow rate times temperature divided by volumetric flow rate. So yes, it makes sense that this is a temperature. And if we think, if we think sort of physically what's going on with here, this is essentially like a weighted average. The outlet temperature is essentially a weighted average of the two inlet temperatures, where the weighting factors, the weighting factors are essentially the two volumetric flow rates, right? So if QV1 is really big compared to QV2, then the outlet is going to be more like T2 than T1, and vice versa. And if you plug in the actual numbers, you end up with 16.7 degrees C as your T3, if you plug in the actual values for these. So hopefully this was a satisfying example problem, and overall a satisfying lecture to help introduce you to the conservation of energy equation as it might be used in bioengineering. Thanks for your attention, and good luck with your study of heat transfer.